Okay, so what is vapor pressure? Okay, the best way to explain what vapor pressure is to look at a very simple picture. So let's say we have a closed container, and inside this container we are able to add some liquid water. So we have liquid water in here. Okay, and let's say we've measured exactly the amount of liquid water that we place in here. Let's say it's 10.25 milliliters. All right, and we say that the temperature we do this at is 20 degrees Celsius. Okay, so let's say we wait for a few days. Let's say a couple days have passed. So let's say 3 days have passed. And we take a look at the volume of liquid inside this closed container of water. When we measure the liquid, and it had 8.25 milliliters of water. Again, the temperature has stayed at 20 degrees. So what has happened? Well, we notice that within the walls of this container, we see water vapor. So we see water vapor. So these are gas molecules of water forming on the side. So we then know, since this is a closed system, we then know we must have 2 milliliters of water vapor that have evaporated from the liquid. So this has evaporated from the liquid. Okay, so as you go from H2O liquid to H2O gas, these gas molecules here are colliding against each other, and also colliding with the walls of the container. So they are bumping into the walls of the container itself. Now these collisions are producing a pressure, a force. And this pressure is called the vapor pressure. Okay, so let's say we wait for another 3 days to happen. So another 3 days have passed. And then we check again at the volume of water inside this container. And there seems to be no change in volume of water and no change in the volume of the vapor. Why? Well, the reason is that there's only so much kinetic energy that 20 degrees Celsius from the surroundings can give to the liquid water. So there's only so much heat that can be given to the liquid molecules so that they will have enough kinetic energy to get into the gaseous state. So remember, liquid water has hydrogen bonding attractions within itself, right? That's why it is in the liquid state. There is hydrogen bonding, IMF. And this heat coming from the surroundings, there's only so much heat that some of the molecules of water will actually now lose this hydrogen bonding. That will go away. And for some of these molecules, once that goes away, they become now gaseous molecules of water. There is no longer an IMF attracting these molecules with each other. But there's only so much 20 degrees can do. It cannot do all of the liquid molecules. So that means that as H2O liquid molecules are evaporating to H2O gas, some of this H2O gas molecules are now being converted back into liquid. Okay? That means that there is an equilibrium state has been reached. And remember, equilibrium means that the forward rate of change is now equal to the reverse rate of change. So since an equilibrium is established, that means that the amount of gas molecules is now at a constant amount, and that can only give a constant amount of vapor pressure. So that is why you don't have all vapor in the container. There's an actual equilibrium that has taken place, as shown here by the double arrows. And for any given amount of temperature, there is going to be equilibrium established, so that for every given temperature, there will be a value of the equilibrium vapor pressure value. So in this figure, I show the different vapor pressures of water at the function of temperature. So as you can see, as the temperature of the water increases, going down, the vapor pressure increases, which makes sense. That means that as you're going from liquid to gas, even though it's in equilibrium, as you're increasing the temperature, you're forcing the forward reaction, so you're creating more H2O gas, which then leads to a higher vapor pressure. So, when you heat the temperature of water all the way up to 100 degrees Celsius, then the vapor pressure of the water, the value here, they don't show it on this table, but the value of the vapor pressure of water is going to now equal the vapor pressure of the atmosphere. So that obviously will go up to 760 millimeters of mercury. When that happens, now that the vapor pressure of water is equal to the atmospheric pressure, then we have no longer an equilibrium. This will all go straight to gas, and we call that boiling. So boiling point is when the vapor pressure of water is now equal to the atmospheric pressure of water, and this was obtained because the temperature of the liquid water was high enough to basically overcome all IMF forces of the liquid. Okay, so now let's look at the amount of vapor pressure released at the same temperature when dealing with different liquids. So different liquids, everything is at the same temperature, but each of these liquids is releasing a different amount of vapor pressure. Why? So looking at this graph, let's take, for example, 20 degrees. So at 20 degrees, which is right here, and the vapor pressure here is on the y-axis. At 20 degrees, we have water, which has a very low vapor pressure, but let's say just water, we can estimate, has a vapor pressure, let's say, of 30 torr. And we have ethyl alcohol, and its vapor pressure at 20 degrees is, let's say, 60 torr. And we look at ethyl ether, and its vapor pressure is higher. It's around 460 torr. If we look at ethylene glycol, which is over on the right-hand side, well, it has no vapor pressure. There is no vapor pressure at 20 degrees because there's nothing above the 0 mark, so no vapor pressure is seen with ethylene glycol. Okay, so let's figure out why. Okay? So why the difference in vapor pressure? Well, from our previous description of vapor pressure from the earlier time in the video, I explained that it deals with the evaporation of liquid to gas state. And it depends, and when you go from liquid to gas state, what is really happening? Well, you're basically reducing the amount of IMF forces. So you're basically destroying a certain degree of IMF. So, as we know from IMF forces, the stronger the IMF, the more energy is going to take to break that attraction. So, if we look at ethylene glycol, and here is the structure of ethylene glycol, again, I can go ahead and that's the organic chemistry way of representing that molecule, but here is ethylene glycol, all right? Of course, we know the H2O. Ethyl alcohol is an ethyl ether is basically 2 carbons and oxygen in the middle, and then 2 carbons. Everything here has hydrogen. Sorry, not on the oxygen. So, like this. Okay, so this is ethyl ether. This is ethyl alcohol. We know, obviously, water, the little structure of water. And this is ethylene glycol. Now, if we look at all these structures, and remember, go ahead and review IMF if you're still foggy on that topic, but if you look at the IMF of this, well, ethylene glycol has hydrogen bonding, and it has 2 areas of hydrogen bonding. So that means ethylene glycol has a very strong intermolecular force. And of course, water, it has hydrogen bonding. Ethyl alcohol has hydrogen bonding, but only in one area. And ethyl ether has no hydrogen bonding. It only has dipole-dipole. Okay? So we can see a trend here. So here I listed again the chemical structures of the liquids on the left, and the amount of vapor pressure they have at 20 degrees, and the type of IMF forces that each of these liquids have. Now again, ethylene glycol has strong, so this is very strong hydrogen bonding capabilities. Of course, water is also strong hydrogen bonding capabilities. Ethanol has hydrogen bonding, but not as strong as water or ethylene glycol. And of course, dipole-dipole is the weakest of all the IMFs here on this table. So, this makes sense because the stronger the IMFs, the tighter the liquid molecules are attracted to each other, which means it takes more energy, more heat, to get these molecules to the gas state. So that's why you need a higher temperature to get a higher vapor pressure. That's why with ethylene glycol you don't even get any gas molecules at 20 degrees. Whereas with ethyl ether down here, you have a lot of it already becoming into a gas molecule state, and which exerts a high amount of vapor pressure. Again, remember, vapor pressure is a function of how many gas molecules are being evaporated from the liquid. As I said before, one of the important things is you can actually figure out what the boiling points of these liquids are going to be at normal pressure levels, at atmospheric pressure. By looking at this graph, you see that 760 torr is right here. Well, 760 torr is equivalent to 760 millimeters of mercury. That is also equivalent to 1 atmospheric pressure, which means this is the pressure that we feel at sea level, standing on planet Earth. So once the vapor pressure of any of these liquids approaches the atmospheric pressure, which is what 760 is, that is when they boil. So looking at the graph, you can actually figure out their boiling points. So when each of these lines intersect the 760 torr, and you go down to the x-axis, that is the boiling point of that liquid. So for ethyl ether, it is going to be around, I would say, like 35 degrees Celsius, right there, because it's right here. For ethyl alcohol, it's going to be right there. So that's about 78 degrees Celsius. We know for water, where the water's line intersects the 760 torr, that is 100 degrees Celsius. Now, we see that ethylene glycol does not intersect the 760 torr till probably when it gets to, if you extend the graph, probably when that line does not extend to all the way out here. So whatever this temperature is, which is very high obviously, this would be then, if you go down, whatever that temperature is, if you go down, that would then be the boiling point of ethylene glycol. So this obviously is very high, and you can look it up on Google. And I just did that, so the boiling point of ethylene glycol is 197 degrees Celsius. So if we would have extended the x-axis, this would be 197 degrees Celsius.